So you just got your thermochemistry test back and maybe you're feeling a bit lost? Hey, don't just toss it in a drawer. That test is actually your single best study guide. Today, we're going to decode the most common mistakes on it so you can build a rock-solid strategy for next time. We have all been there. You're staring at the red marks and you're just thinking, wait, I thought I knew this. You see the right answer, but the path to actually get there, it feels like a total mystery.
Well, the good news is you are so not alone. These are classic trip-ups that almost everybody makes. And you know what? Because they're common, they are totally fixable. So let's break them down together.
Okay, first things first. This is not about memorizing what you got wrong. No, this is about building a whole new strategy, learning how to spot the hidden traps in these questions so you can walk into the next test feeling way more confident. All right, let's dive right into our first big topic, those energy diagrams. Specifically, what on earth happens when a catalyst shows up? This is a huge source of lost points, so let's nail this down right now. The number one mistake is seeing two different paths on the diagram and assuming the final energy change, that's our good friend delta H, is different. That is the trap. Think of it this way. A catalyst offers a shortcut, but it doesn't change your destination. This table just breaks it down perfectly. Look, the start and end energies are exactly the same for both paths. The only thing that changes is that big peak in the middle, the activation energy. A catalyst just makes that hill smaller, creating a faster, easier route. The start and end points, they don't move an inch. So, let's burn this into our memory. A catalyst does not change the reactant energy, it does not change the product energy, and it absolutely does not change the overall delta H. All it does is speed things up. That's it. Okay, let's move on from the diagrams and get into the numbers. Our next topic is bond enthalpy. I want you to think of this like chemical accounting. You've got your costs and you've got your payoffs. The process here is absolutely key. First, you add up all the energy it costs to break every single bond in your reactants. That's your investment. Then, you add up the energy you get back when new bonds are formed in the products. That's your payoff. And finally, and this is the crucial part, you subtract. It's always bonds broken minus bonds formed. And here it is, the giant red flag. If you find yourself just adding all the numbers together, you've taken a wrong turn. It's so tempting to do, right? But you've got to remember, bond enthalpy is always a subtraction. It's the energy you put in minus the energy you get out. And hey, here's a little pro tip for you. Don't get lost in the weeds with the math. These bond enthalpy values are just averages anyway. So before you even start calculating, ask yourself, is this reaction going to release heat or absorb it? Just figuring out if the sign should be positive or negative can often help you eliminate half the answers on a multiple choice question right away. All right, our next section is all about the rules of the game. We're talking about mastering those core definitions. These are easy points to get if you know them, and, well, really easy points to lose if you don't. First up, enthalpy of formation. Look closely. See that part in bold? 1 mole. The entire definition of enthalpy of formation hinges on that single detail. It is the energy change when you form exactly 1 mole of a product. This little detail is how they'll try to trick you. And here is that classic trap in action. A question gives you the delta H for a reaction that produces, say, 2 moles of ammonia. The mistake is just grabbing that number and calling it the enthalpy of formation. But wait, remember the rule from the last slide? The fix is actually super simple. Since the definition is all about 1 mole, you just take the total delta H for the reaction and divide it by the number of moles of product you actually made. It's one quick division that saves you from a really common error. Okay, next up is Hess's law. Now, I know this one can look really intimidating with all those different reaction steps, but don't let it fool you. It's just a puzzle. Your job is to take the puzzle pieces they give you, those individual reactions, and arrange them to build your target equation. Here is your 4-step game plan. First, line everything up to match your target. Second, if you have to flip an equation around, you must also flip the sign of its delta H. That's a big one. Third, cancel out anything that's identical on both sides. And finally, just carefully add up what's left. Follow this checklist, and you'll be golden. So, we've broken down catalysts, bond math, and some really key definitions. But what's the big picture takeaway from all this? It's about more than just dodging mistakes. It's about a total mindset shift that builds real, lasting confidence. So, here's the final piece of advice. Thermochemistry isn't really a math test, it's a logic test. Instead of just trying to memorize formulas, focus on the why. Why does a catalyst only affect the path? What's the process for bond accounting? What's the exact rule for enthalpy of formation? When you master these core ideas, the math just kind of follows. So I'm going to leave you with one final, really powerful question to ask yourself on your next test. Before you even pick up your calculator, just pause and ask yourself this. What is this question really testing? Are they testing me on catalysts, on the definition of formation, on bond enthalpy subtraction? If you can identify that core concept first, you've already won half the battle. And that, right there, is the key to unlocking the right answer every single time.